Hello friends. So today we are going to talk about the generation recombination process in the PN junction. So let us consider the first the generation current under the reverse bias condition. Means positive voltage is applied on the n side and the negative voltage is applied on the p side. So that what will happen, the depletion layer will go on increasing on the both side because of the positive charges will be attracted towards the negative side of that potential and the other side. Okay. So because of this what happens, actually the reduction in the carrier concentration uh, under the reverse bias condition. So there is a reduction in the carrier concentration, that is Pn is very less than Ni square. Okay, this condition getting satisfied. Okay, so the dominant generation process are of the that of the emission only. So the emission processes are dominant here. Emission processes are dominant here. Okay. So under this reverse bias condition. Okay. So the rate of generation of this electron hole pair, okay, rate of generation of the electron hole pair, it can be also called as the EHP, electron hole pair. Okay, can be calculated from the one of the equation which we have seen in the last chapter, that is nothing but the U is equal to sigma n sigma p Vth upon n into Nt into Pn minus Ni square and some complicated denominator factor. Okay, so this is the one of the equation from the chapter number 1 of the SMG's book. So this is with now within that equation what we are going to talk about, the we will additionally have the some conditions over here, and that condition are nothing but the P is very less than the very less than the Ni, and N is also the very less than Ni. Okay, intrinsic carriers within it are very less on the hole concentration and the electron concentration. So that will give us the generation rate U is equal to, okay, negative of this is sigma p sigma n phi th into nt. Nt is the tap state density upon sigma n into exponential of Et minus E I upon kt plus sigma p exponential into the ei minus et upon kt. So this is the equation, can get it into Ni component. Okay, Ni. So this can also be defined to be the nothing but the minus Ni upon 2g. Okay, so 1 over 2g is nothing but this whole bracket term, and what we call it as the generation lifetime. Okay, so the 2g is generation lifetime. Okay, so its reciprocal of that is given by. So the current due to this generation in the depletion region is given by, so the current due to the generation, okay, the current due to this generation in the depletion region, it is given by the equation, that is current density due to the generation is given by the 0 to Wd into Q generation rate, its mod value into dx is approximately equal to Q times generation rate into Wd, because dx only, because they are the independent of the x. So whatever the equation we got, it nothing for the Q u into Wd. So what we can have, we know the equation for the u, that is mod of this will give us the Ni by 2g. So generation current is given by Q W d into Ni upon 2g. So, this is equation number 2 I can call, and this is equation number 1. So, here the WD is the depletion layer width. If this if the generation lifetime is a slowly varying function of the temperature, then the generation current will have the same temperature dependence as the Ni. So, what is happening here means if the generation lifetime is slowly varying function of the time, okay, then the obviously this is also the temperature dependent. So, both will becomes temperature dependent also. So, at a given temperature, okay, at a given temperature, given T, okay, generation current Jg is proportional to the, it is proportional to the depletion width, okay. So, this will be proportional to the depletion layer width, okay. So, which in turn is the dependent on the applied reverse voltage. So, this will again because the WD will be proportional to the applied voltage, as we have seen in the earlier processes, something like abrupt junctions and the linearly graded junctions. So, this generation processes will be dependent on the reverse bias potential, because we are talking about the reverse bias condition. So, JGE can be proportional to the psi bi plus V raised to 1 by 2 for abrupt junction. And so, this is equation number 3 I can call, and Jg also for the linearly dependent linearly graded junctions, its proportionality is a different one. So, psi bi plus phi raised to 1 by phi is nothing but the applied potential across it. Okay. So, now the let us talk about the total reverse current. So, the total reverse current uh, for the given condition, okay, can be approximated by the sum of the diffusion component in the neutral region and the generation current in the depletion region. So, the what we can have here, the it is just the sum of the diffusion component in the neutral region, because the other than the depletion width the other remaining part is the neutral region, and the generation current in the depletion region. So, both the components we are just trying to combine them together. So, this is generation current is equal to q times square root of dou dp into divided by tau p Ni square upon Nd plus, now this is nothing but the diffusion component plus the other is the generation current in the depletion region. So, that is q Ni Wd upon 2g. This is what here we have seen here. So, this is generation current component. So, this is equation number 4. So, now for the semiconductors with very large values of the Ni, okay, for the large Ni, okay, such as the germanium, the diffusion component will be temperature dependent. Obviously, at the room temperature, and the reverse current will flow follow the Shockley equation and so on and so forth. So, and that will be the temperature dependent phenomena when the diffusion component is considered, and at the room temperature if we just try to consider, and corresponding the reverse current, that will follow the Shockley equation. Okay. But if Ni is a small, okay, so for the large Ni it follows Shockley equation, okay, and for small Ni, okay, the generation current may dominate. Okay. So, the generation for the small Ni, generation current dominate, generation current dominant. So, yeah, at sufficiently high temperatures, the diffusion current will also dominate, because the that will increase the diffusion within that neutral region. So, at high temperature, diffusion component or diffusion current dominate, actually diffusion current dominate. Okay, do remember these things. Okay. So, now this is the case for the reverse bias case. Now, at a forward bias, what happens that at forward bias with the major recombination generation processes in the deflection region are the capture processes. Okay, so the I can just call it as the recombination, and generation processes are capture processes. And this is something like OJ electron capture and so forth, that will come. So we have the generation current, that is in the addition to the diffusion current. So we have the we have here the generation current in addition with the what we can say, the diffusion current. So let's try to substitute this equation, that is for equation for the Pn. Okay, where we have here sorry, Nt, and the that is from the equation number n. Okay, so in this equation, so try to substitute the value of the Pn. Okay, and that Pn equation is given by the Pn is equal to Ni square exponential of EFn minus EFE. This is quasi Fermi energy for the electron, quasi Fermi energy for the n region, and the quasi Fermi energy level for the p region. So this is something like the applied potential, of course, that is a QV. So just try to substitute the Pn value in this equation and try to rewrite that equation. Okay, and so what we will get it is nothing but the generation current is generation rate is equal to sigma p sigma n phi th n t ni square into exponential of qv by kt minus 1, because ni square can be taken common out of it, and just rewrite the equation, and what we will get it is nothing but the sigma n to n plus ni into exponential of et minus ei by kt plus sigma p into p plus pi sorry ni into exponential of ei minus et by kt. Okay, so this is the equation we can get it. So this is equation number in condition, equation number 5 we can have here. So now under the assumptions that Et is equal to Ei, okay, suppose Et is equal to Ei, this is the assumption we are just making over here. So assuming what we are assuming here, that is nothing but the Et is equal to Ei, and with sigma n is equal to sigma p is equal to sigma. What is this? This is nothing but the conductivity of the holes, conductivity of the electron, conductivity of holes, both are equal, that is equal to sigma. So the above equation will reduce to the u is equal to, okay, this above equation means this equation. So this is equal to this. So what will have e exponential raised to 0 will give us the 1. So n plus ni into sigma n, but sigma n and sigma p are both are same, so that is sigma. So the one of the sigma will get cancelled out, and n plus ni and p plus ni. So what will get it? N plus p plus 2 times ni, and that will give us the equation is nothing but the sigma, one of the sigma will get cancelled out, then phi th nt ni square into exponential of qv by kt minus 1 divided by n plus p plus 2 times ni. So this is given in terms of the n and p values. We can substitute over n and p values can be substituted, that is n is equal to ni into exponential of efn minus ei upon kt and so on and so forth. So we will try to substitute that values, and what we will get it nothing but sigma phi th nt ni square exponential of qv by kt minus 1 upon ni. I will just take out common because here also ni and here also ni. So, ni I will just take out common. So, exponential of EFN minus EI by kt plus exponential of EI minus ET by kt plus 2 because ni has taken common out of it. So, this ni will get cancelled out to one of the ni, and so the maximum value of the u exists. Here we can have this should be the minimum, this should be the minimum one. So, exists in the deflation region where the EI is a halfway, EI is the halfway. At that time we will get the maximum value of the generation current, that is u or generation rate. So, EI is a halfway between the okay. So, maximum u when EI is halfway between what? EI, EFN and EFP, EFN and EFP. So, the denominator in the above equation can becomes 2ni times the what we can have halfway means okay, we can have this suppose somewhere value, then this denominator will get is the because EFN minus EFI that is halfway. So, EF can be EFN minus EI can have the QV value. So, QV by 2 KT. So, what we will get it is nothing but the denominator. Okay. So, denominator in above equation is equal to 2 times ni into exponential of qv by 2 kt plus 1, okay, because 2 is taken out. So, and we can obtain for the for V is very greater than the kT for the thermal energy, kT by q charges is there. So, the generation rate is approximately equal to half sigma VTH NT Ni sorry small ni into exponential of QV by KT, QV by KT. So, this is the equation number, I can call it as this is equation number suppose 5, I guess 6. This is equation number 6, this is equation number 7 for the equation. So, the generation current, so the JRE is equal to integration from 0 to WD. Substitute the value of the U here, Q mod U is U dx is approximately equal to QWD upon QWD upon 2 into sigma VTH NT Ni exponential of QV by KT TQV by 2 KT, so on and so forth. So, this is approximately equal to into dx. So, the dx is there. So, as already WD is there. Okay, integrate after the integration. So, this can be equal to QWD Ni upon 2 tau, another parameter has arrived, upon exponential of QV by KT, is equation number 8. Here this what here assumes this here we have the assumed that the most part of the depletion layer has the maximum recombination rate, and this JRE, that is current recombination current, is somewhat an overestimate. So, a more obvious derivation can give us the JRE is equal to integration from 0 to WD QU dx u dx, and that will give us the, this is approximately equal to root pi by 2 k t n I upon 2 exponential q phi by 2 k t. So, this is equation number 9. Where epsilon 0, where epsilon 0 is electric field at the location of, at the location where we can have the maximum recombination, location at maximum recombination, and it is equal to, nothing but the q times n into 2 times psi b minus phi upon epsilon s. Okay, so this equation number 10. So similarly, we can get the generation current in the reverse bias. Okay, similarly, we can have the generation current, okay, generation current in reverse bias, because we have seen for the forward bias case, right? So domination current, what we, where we have assume that the here, okay, for the forward bias case we have calculated the current. So the, for the reverse bias we can have the recombination current in forward bias is proportional to the Ni. So the total current can be approximated by just summing both the equation, that is Jf is equal to JRE plus JGE. So what we will get it is nothing but the q times integration of d q into root of dp upon 2p into ni square upon nd exponential of qv by kt, plus other term is nothing but the root pi by 2. This is actually this term, and the another term is here root pi by 2. I am just trying to substitute this value over here. So kt times ni upon 2p E0 into exponential of qv by 2 kt. So this is what we can get it, and if we just try to try to look at the experimental results. Okay, so at the experimental results is represented by empirical formula. Now what is that? It is nothing but the Jf is proportional to the exponential of qv by eta kt. Okay, so what it gives us, this eta factor have the values, if eta is equal to 2 we can get the recombination current. Okay, recombination current is a dominant one, recombination current. In case of the eta is equal to 1 we can have the diffusion current. Okay, diffusion current, and if suppose its value lies between 1 and 2, then obviously the recombination current and the diffusion current both are contributing to its current. So this is something like, okay, both are comparable in that case. So this is what we can call it as the generation recombination processes.